Welcome to today's discussion of tests of significance. This is the beginning of our discussion of various inferential statistics tests. And as you'll see, there are a variety of tests, and we'll look at the rules for when to use which kind of test and depending on your data and research design over the next few chapters. In today's discussion, we're going to focus on the hypothesis testing model and the most basic test using that model, the z-test. And we'll talk a little bit more about a couple other tests too. But first, let's look at an overview of this section. In our previous unit, we were estimating parameters from data and getting the margins of error. Now, we're looking at testing, and this helps us answer another kind of question, specifically hypothesis related questions. For example, is a parameter equal to some pre-specified value or isn't it? Previously, we estimated the confidence of, or we could estimate values in a level of confidence in them, and you'll see how estimation and testing are related, but the goals are different. With a test of significance, we are looking at whether the observed difference was due to chance or to something else. And the primary way we'll quantify this is through looking at how the observed value compares to the standard error. So if an observed value is too many standard errors away from its expected value, then that's very hard to explain by chance. However, if an observed value is close to the expected value and not many standard errors away, then we would consider that a non-significant difference. So it's not, statistically, the numbers aren't different. And there are several different tests of significance. The appropriate test to use depends on multiple factors, especially those related to the research design and sampling of the study and the format of the data of interest. To help flesh this out, let's look at an example. We suppose there's two investigators and they're arguing about a large box of numbered tickets. And they have fun names, Nullsheimer and Altshuler. And you'll see this maps onto our hypothesis testing model. Nullsheimer says the average is 50. Altshuler says, well, the average is different than 50, but they don't know for sure. So they finally get tired of arguing and they look at some data. And since there are many, many tickets in the box, they take a sample and draw 500 tickets at random. The average of that draws is 48 with a standard deviation of 15. Now, our goal is to determine if the difference reflects chance error or whether the average for all the tickets in the box was really different from 50. Thus, is the difference between the 48 that we drew, is that just a chance error difference from 50, or is this is the box actually have a different average? To help us understand this, we use the null and alternative hypothesis. And these hypotheses are statements about the box, not just the sample. And each hypothesis represents one side of the argument. So looking back at our previous example, in the dialogue, Nullsheimer is defending the null hypothesis. According to him, the average of the box was 50. The sample average turned out to be lower than 50 just by the luck of the draw. And that's the argument of the null hypothesis. While Altshuler argued for the alternative hypothesis. She said that the average of the box is lower than 50. And her argument in a nutshell is that the sample average is so many standard errors below 50 that Nullsheimer almost has to be wrong. They couldn't agree about the data after setting out their hypotheses. They agree about the data themselves. They both agree the standard, the average they observed was 48. But they disagree about the box that the average comes from. Does the box really have an average of 50? And that's the true average of the box, or is it lower than 50? And this is at the core of the idea between the null and alternative hypothesis. And these are really important to understand. We will use the null and alternative hypothesis for virtually every single problem we do in this whole unit. And essentially, the null hypothesis always says an observed difference is due to chance. The alternative hypothesis says that the difference is real. Sometimes people find the terminology difficult to deal with because the alternative hypothesis is often what someone sets out to prove. And then the null hypothesis is the alternative for the findings in terms of chance variation. But that's while that might conceptually fit with how you think about the hypotheses, the terminology here is completely standard. These are always called the null and alternative hypotheses. This is whereas sometimes we've discussed how there can be different jargon for certain areas that we've looked at on certain topics. This is not one of those topics. Hypothesis testing has a very standard set of terms, ideas, and methods, and the null and alternative hypotheses are very much at the core of that model. It's important to remember that a box model is very important in your test of significance. The test gets at the question of whether the observed difference is real or just chance variation. And a real difference is one that says something about the box itself. It says this population is different. It's not just a fluke of sampling. And so that's why it's important to keep the box model in mind and keep using it when you're solving these problems. For one, it's conceptually important, but also in that it's conceptually important, it will help you to get to the correct null and alternative hypotheses and then the right test choice, as you'll see once we accumulate a few different tests. In addition to the null and alternative hypothesis, we have test statistics that we use to measure the difference between the data and what is expected based on the null hypothesis. The first test statistic that we encounter is the z-test. And in this case, the z-value says how many standard errors away an observed value is from its expected value, and where the expected value is calculated using the null hypothesis. This is the case for this first kind of test we're looking at, which is a z-test. I would say this also could be referred to as a one sample z-test. You have a sample, and we're comparing it to some known information about the population relevant to that test. As you can see, the z-statistic takes a familiar form. Observed minus expected divided by the standard error. So this looks very similar to the standard unit conversion or z-score equation that we looked at before, where The difference being that now we use the standard error in the denominator rather than the standard deviation. And we need the standard error here because we're dealing with a sample. And remember that the square root law is an essential part of how we quantify correctly the effective sample size on the estimation of chance variation, or the standard error. To think back to our previous example, it was the null hypothesis that told Altshuler to use 50 as the benchmark, not some other number. He set up the null hypothesis that the box is equal to 50. That's the exact point where the null hypothesis comes into the procedure. If there was different information about the box or another reason for a different null hypothesis, then testing that hypothesis would give a different benchmark in the numerator of Z. So it's important to use the right information when you're setting up your null and alternative hypotheses. Furthermore, the null hypothesis did not tell us anything about the standard deviation of the box. The null hypothesis just pertained to the average of the box. And the standard deviation of the box is estimated from the data to help us compute the SE that goes into the denominator. When they did the example we're looking at, which is at the very beginning of chapter 29, if you want the more extended version, but we're going to do a lot more examples today too. You can see that they took the observed value, subtracted, which was 48, remember, and then the expected value was 50, and divide by the standard error. And when they do that, they end up with a z-score of -3. If we look at that z-score on a standard normal curve, and use what we know about the normal curve to help us interpret these findings, we know that the probability of getting a z-score of -3 is 1 in 1,000. It's extremely small. So this, in the context of the example, this Z statistic should tell the Dr. Nullsheimer immediately that there's a problem with his hypothesis. Why should he be stopped in his tracks conceptually? Because the probability of this score is just ridiculously low. The area to the left of -3 under a normal curve is so small that the chance of getting this value is extremely low. And as you'll see, we have established levels for our significance levels in deciding whether a result is statistically significant or not, although there is some room for interpretation, as we'll discuss later on, with respect to how you set up your decision rule for what's the cutoff for a significant test or not. To review, when we make a test of significance, we use a standard process. You set up the null hypothesis in terms of a box model for the data. So this first step is setting up your box model and figuring out the null hypothesis, as well as the alternative hypothesis. But remember, the experiment is always conceived of in terms of the null at several steps. So once we have ascertained the null hypothesis, we pick a test statistic to help measure the difference between the data and what's expected based on the null hypothesis. Now, how do we choose a test statistic? Well, right now, we only have the one test statistic to look at, our z-test, but very shortly, we'll have several test statistics to look at. And so you can choose among them by looking at essential factors in the experimental design or the box model and the format of the data. And so based on those two basic areas, you'll be able to use the standard kind of process to help you figure out what kind of test do we want to use based on our data. And don't worry, there's not too many tests. We're only doing a handful of tests, some of which you have actually already encountered before. You just don't know it yet. So you'll pick a test statistic, and once you've done that, the next step is to do the analysis, which lets us compute the observed significance level of P. We do the analysis of our test statistic, arrive at an observed test statistic, or a statistic refers to, as a term, both the formula or process used to find the test statistic and the number itself that's found. So, for example, this is a test statistic here, the Z statistic, which is defined as observed minus expected over standard error. And -3 is an observed test statistic. We did a Z test, we found this value. So just a heads up that we obviously use the word statistic and statistics in a variety of ways, but I want to draw your attention to this one at the moment. And when you come up with your observed test statistic, then the next step is to compute the observed significance level for P. And then based on the observed significance level, you decide whether to retain or reject the null, so which is the next step is often called, where you decide, is this result statistically significant or not? We say if the P is less than 5%, it's statistically significant. And this is a general rule that's more usually observed across lots of fields and generally in the research literature. Although there's some variation on that, again, depending on certain other constraints about sampling and data. But for our purposes, we're going to generally look at P as less than 0.05 as the borderline where we say a result can be statistically significant or not. We normally just say significant, not statistically significant over and over again. And please don't, especially in your anything. It just the point it's understood when you're writing about statistics that when you use the word significant, you're referring to this kind of significance. We in statistics don't use the word significant in other contexts, at least when writing up results. We say that if it's the P is less than 1%, the result's highly significant. Again, as we'll see, the relative significance or the relative difference between these two levels depends on more factors than just the p-value. Sometimes if you have very large samples, you're more likely to get smaller p-values, and it might not reflect as big a difference, even if or it might not reflect an especially big difference, but there's an effect of having a very large sample. And a smaller sample makes it harder to in a variety of ways, see a statistically significant result. Let's leave it at that. So even with a small sample, if you have a P close to, at about 0.05 or 5%, that's often pretty important. So let's look at an example here to help us practice going through this hypothesis testing process. Oh, here we go. So this problem has it's a nice, simple scenario for us to use for our hypothesis test. We're told many companies are experimenting with flex time, allowing employees to choose their schedules within broad limits set by management. Among other things, flex time is supposed to reduce absenteeism. One firm knows that in the past few years, employees have averaged 6.3 days off from work. This year, the firm introduces flex time. Management chooses a simple random sample of 100 employees to follow in detail, and at the end of the year, these employees average 5.5 days off from work, and the standard deviation is 2.9 days. Did absenteeism really go down, or is this just chance variation? We can formulate our hypotheses and answer this question using the hypothesis testing model. If we first think about this in terms of our box model, this is like a box where the entire the number of tickets in the box are however many employees are at the company, and each employee has one ticket in the box. Their ticket has on it number of absences, or their number of days off work. From this box, we sample 100 employees. And we're told that they're chosen at random. So that's important information. This is a simple random sample. So we know it's okay to go ahead with the z-test. If this was not a random sample, we could not use this test. Yeah, sorry. Furthermore, we know some other things about our general model. We're told that the firm in question knows that in the past years, employees have averaged 6.3 days off from work. This is really important information because this is a key statement telling us that this is an information we already know. So as you'll see, this is part of how we know to do one sample z-test here. And in this model, our expected value, oh my gosh, I can't do that right now. Our expected value is equal to this population parameter that we've been given. The expected population parameter of 6.3 days off from work. Now we can set up our null hypothesis. In this case, the null hypothesis is that the average of the box is 6.3 days. And sometimes these are written symbolically. I could say then that the average for the box is equal to 6.3 days still, of course. I was writing this in alternative symbolic language. I know some of you really like the formulas. The null hypothesis always says some version of the sample and the parameter are the same, the two samples are the same. Basically, there's no difference. And our alternative hypothesis is that the average is below 6.3 days. Okay? We're given some important information. Let's collect that over here to help us with our analyses, because at this point we know we have an expected average, and we know that we are testing it against our observed value against this expected one that we already know. So let's collect everything. We need to have the observed and expected value, the standard deviation, which is given here. If it wasn't given, we couldn't actually find it from this information because we don't have enough data here. But sometimes if you're not given the standard deviation, don't jump to conclusions. Make sure you check, because with a 0, 1 box, you can get the standard deviation through the shortcut without having all of the individual data. So we've collected some important terms, and let's go ahead with our analysis. We can find technically we need the SE. So let's go ahead and we'll find that first and then plug it in. We know that the SE is the square root of our draw is 100 times the standard deviation, and it's going to be equal to 0.29. Days, of course. And we can just use our z-test formula. Z is equal to observed minus expected over the standard error. Our observed value is 5.5. Our expected value is 6.3. We can go ahead and divide that by our standard error, 0.29. And when we do, you'll get a z of approximately negative 2.8. And you can look up a z-score of negative 2.8 in the your z table and get the exact probability here. In this case, it's 0.3% of 1%. It's very small. But we're not done. That's the thing here. The really key part of hypothesis testing is, of course, doing this whole process we just laid out. Yes, that's essential. But there's one more step that is essential. And that is you need to decide about the hypothesis. And in this case, we're given a specific question. Did absenteeism really go down, or is this chance variation? Sometimes they'll be just given a scenario and asked if there's a difference. The point is that you need to decide whether the null hypothesis is true or not. We say the null hypothesis is true when p is bigger than 0.05. We say it's false, or we reject the null when p is less than 0.05. In this case, p is far less than 0.05. It's minuscule. So we would reject the null. And you need to write a sentence to describe your findings. We can describe that sentence, and we're given a clue here about how to frame it with this question. Did absenteeism really go down?
Number 7.
Chance variation.
But I don't know. 482, chapter 26. What the hell? Okay.
Okay. So to write our sentence, let's decide about our. Okay. Let's decide about our question here. Did absenteeism really go down, or is this chance variation? What do you think? These results tell us that absenteeism really went down. This isn't just chance variation. We could say it was chance variation if our results were in the range expected by the null hypothesis. To describe this sentence, we want to make sure our result sentence for this, we want to make sure to include describe our sample, compare it to the population, and in a way that encompasses the study. So we could say employees had fewer absences with flex time, and the mean for that group we give in parentheses, just like we did in our lab report for assignment 3 or lab 3. Our mean was 5.5 days. I'm just calling the standard scheduling standard practices in this case. And the mean for that group is 6.3. And at this point, there's this last bit that we put in, comma, after that last part. I don't know if you can see it, and I know I'm pretty far down on the screen here, sorry. We give the value of our z statistic. So z was negative 2.8, comma, the p-value, which we know is 0.3% of 1% in this case. It'd be fine to express that in a normal form too. But key things being here in the sentence, we have to include the group that is studied our sample, their mean, how they compare to the other group, in this case our standard practices, and their mean, and then comma the z-statistic and the p-value. This is a standard format for writing up your results. And we will practice this more. So don't worry, we'll practice sentences some more, but this gives us a whole model for doing this problem. And you can repeat this problem with a different sample average and see how it turns out if you like. We're going to move on now and take a look at 0-1 boxes. This is another application of the z-test. If you're classifying and counting the values in your variable, as in there are zeros and ones in the box, then you can use the z-statistic still to help you test the difference between your observed and expected values. The test still follows the same basic format, except now we instead use the z of the observed number minus the expected number over the standard error for the number. So instead of using the means, we use the numbers. Most of the calculations and many things for dealing with a 0-1 box are just like similar to how we dealt with our 0-1 boxes in our previous unit. Let's just pause for a minute and think about how we have some different pathways going here. And we'll see this fleshed out a little differently at the end, but you can see that data comes in multiple formats. It's generally quantitative or qualitative. Quantitative data is like interval or ratio level data. Interval ratio data is generally considered quantitative. Now, it's possible, as you know, to recode data. You could turn your interval or ratio data into groups and then classify. You could classify and count. And then the data is qualitative. So anytime we are classifying within the variable and counting, that's qualitative data. The big, an important thing to remember when you're dealing with qualitative data is that the values of the numbers aren't significant in and of themselves. They're just numbers that are used as codes, like where we call males ones and females zeros to help us estimate the number of males expected from some sample data. When you have qualitative data, which is generally nominal, ordinal data can be treated in different ways. So depending on your ordinal data, you might consider it quantitative or qualitative. I'm not going to give you anything tricky on this respect, but if your ordinal data follows a scale that where you can infer that the differences are approximately the same between the values, like strongly agree, agree, neutral, disagree, strongly disagree. We could consider that that's ordinal data technically, but we can, since it is reasonable to assume that the differences are the same between those levels, it's often considered interval data, for example. Nominal data is always qualitative. And based on the type of data you've got, you can get different statistics to help you summarize the data. You can get, if it's quantitative, you can use the sum or the average. You have to have interval and ratio data to get sums and averages. Otherwise, these numbers are meaningful, or they're only meaningful when you have quantitative data. When you have qualitative data, you can only get a number, a count, and a percentage or a proportion representation. We also have two different ways to get to the SD. Sometimes it's given to us, and sometimes we have to estimate it. So it's important when you are setting foot on your decision-making trail to assess your data, your variables for what kind of variable is this, what kind of data am I dealing with, and is the standard deviation given or does it need to be estimated? As part of a statistics project in the early 1970s, Mr. Frank Alpert approached the first 100 students he saw one day on Sproul Plaza at the University of California, Berkeley, and found out the school or college in which they were enrolled. There were 53 men in his sample. From the registered data, 25,000 students were registered at Berkeley that term, and 67% were male. Was his sampling procedure like taking a simple random sample? Well, I already have a pretty good idea that it's not, because it says that he approached the first 100 students he saw one day. So that's clear selection bias. But we're asked not, was this a simple random sample? Was his sampling procedure like taking a simple random sample? What's the difference? Because the question is, was his sample different than what we would, did he get different data than what we would expect if we did a simple random sample? And filling in the blanks in this, I thought, would be a fun exercise to help walk us through the box model for the null hypothesis here. In this, of course, we have a classifying and counting scenario. So, although I think I just gave away one of our spots. So there's one ticket in the box for each, which one here? Each person in the sample or each student at Berkeley? Let's do some voting. Wake up, fill in a blank. There's one ticket in the box for each person or every student at Berkeley. We got it. Yes, the student registered at Berkeley that term. Yep. Because the box is our population. In this sense, and it's got 25,000 tickets. And how are those tickets marked? One of these blanks gets it. Does this blank get a 1 or a 0? The ticket is marked 1 for men, and correspondingly, it's marked 0 for women. This isn't a social judgment. We're doing that because we're testing the proportion of men against the known proportion of men. If we set up the question in the opposite way, and we were told that 73% were female, we would make the women 1 and the men 0. So, oops, I already told you the number of tickets in the box is 25,000. So the number of draws is clearly 100. The null hypothesis says that the sample is like a number blank made at random from the box. Is like blank blank made at random from the box. In this case, it's just sort of a repeat of what the earlier one, stepwise through this. The null hypothesis, it says the sample is like 100 draws. We're just relating it to the box. The sample is like 100 draws made at random from the box. And the percentage of ones in the box is already known to us. What is it? 67%. All right, thank you. 67%. And so this is a nice process leading you through the finding the box model for the null hypothesis. And you can continue it by, we can go through the step-by-step to the Z. The observed number of men is, was it 53? Oops. I recall. The expected number of men would be the proportion that is in our population, 67. And these correspond to the proportions because they just did a sample of 100. If the null hypothesis is right, the number of men in the sample is like the sum of the draws from the box or the average. What do you think? Well, this one I knew is a little tricky. In this case, we are back to classifying and counting. Remember, our box is zeros and ones, where the ones are men and the zeros are women. So we are getting the sums of the box. The standard error for the number of men is something we can find. We just have to estimate we need to collect some terms here because we don't have the standard deviation, and we know to get the standard error for the number, we need to get the standard deviation. How are we going to get the standard deviation? Well, we're going to use the standard deviation shortcut. I keep doing that times the small fraction. And this is going to cancel out 1 minus 0. And the square root, we know our big fraction is the proportion of men in the sample, in the population. And that's 0.6. Always be careful. One error begets another. So we're looking for the standard deviation in our population. And here we've got our 0.67. We're going to multiply it by the small fraction, which was 0.33. And we end up with a standard deviation of approximately 4.7. We can get the standard error using the square root of our draws times the SD. So we've got the square root of 100 times 4.7. And we get a square root of, I jumped a step here in my notes, sorry. We end up with a standard error of 4.7. The standard deviation, I forgot to write down the subproduct for that. It's, let's see. Of course, it's 0.47. There we go. Oh no. I thought that seemed like too big a number. So we end up with a standard error equal to 4.7, and we can just finally do our z-test. In this last step, so our observed value is 53. The expected value is 67. Our standard error is 4.7. We end up with a z-score of approximately -3. And the p-value here, remember, the z-score for -3 has a p-value equal to 1 out of 1,000. It's always the same. Every time you get a z-score of -3, it will always have the same p-value. Always. Without fail. So we can, now if we go back, we know that this p-value is very small. It's less than 5%. So that would tell us to reject the null, which in this case, our null hypothesis was that his sampling technique was like taking 100 samples randomly, but it wasn't. And if I want to write this sentence well, then it's really important to go back and remind myself of what the question was. Was a sampling procedure like taking a simple random sample? Okay. And we're quantifying that by the number of men. So in this case, I could describe the results of our test by saying that the I'm going to say the proportion. You could say the percentage, or I guess we'll do that because we normally have been using percentages. Okay, so you can see I wrote out my sentence here. And a couple things to highlight about it. The percent of men in the sample, which is a primary data point we're interested in analyzing here, was lower than the percentage of men expected through simple random sampling of the UC Berkeley population. This all came from, this was what we, first, the percentage of men expected was the comparison group through simple random sampling of the UC Berkeley population. And this is a more detail about the comparison group. We're comparing it to what would be expected based on what we know about this population. I give the percentages for each group, and Z equals -3, comma, P is 1 out of 1,000. You could also say P is equal to 0.0001. And there you have it. And we could finish filling this in up here. The SE for the number of men is 4.7, and the Z is -3. E is 1 out of 1,000. It's very, very good practice when you're doing these problems in the tests of significance section. I cannot strongly enough recommend that you go that last step of writing and trying to write an example sentence. Do your best. You have to write lots of sentences in order to start getting this right. Just like everything else, you have to practice to get it right. So practice writing the sentences, because you will have to write sentences on the final exam as part of the results. It's also part of our last lab. It's an essential part of inferential statistics, because reporting the statistics in a way that is key thing here in terms of the variable, not just saying the observed value is lower than the expected value. It needs to be in terms of the variable and the study format. Very, very important. There's lots more problems. We don't have time to do them. We're going to do more problems in a moment from our review exercises. But first, let's discuss quickly the t-test. The t-test is very similar to the z-test, except that we use the t-test when we have small samples. That's because with the small samples, the z-test has to be modified. It just doesn't give an accurate assessment of the probabilities. And I'm not too concerned about the rest of the mathematical discussion about that. You just need to remember, if you have a small sample, and then you need to use the t-test. You can use the z-test for a large sample. We're going to say about 25 people or less requires a z-test, or excuse me, requires a t-test, and larger samples can use the z-test. The real issue between the tests is although they follow the same format, the t-test still follows this observed minus expected over the standard error, but now we need to adjust our estimation of the standard deviation, because the number of measurements is so small. The estimate could be way off if we just had the number, we just used the normal practice for getting our standard deviation. We have extra uncertainty here, and we need to take it into account by first using the SD plus. The SD plus is a larger estimate of the standard deviation. You can see how it is linked directly to the regular standard deviation, but in this case, we adjust our standard deviation by this factor of the square root of the number of measurements over the number of measurements minus 1. It works. Once you have your SD plus, then you can just find the standard error the normal way we always find the standard error. And the other difference with the t-test is in the p-value. With a small number of measurements, you have to use the student's curve and or the t-distribution. You see this referred to two different ways. The reason it's called the student's curve is because the man Gossett, who came up with this test, published under the pen name student because his employers didn't want competition to realize how important his work was. And so you often see this called the student's T. So that's why no more mystical meaning there, like related to your use of it or not. But The key thing about the student's curve is that you have to use degrees of freedom. So technically, there are different curves for each degrees of freedom, but usually in a t-table you can just look up your appropriate degrees of freedom and find your p-value. The degrees of freedom are, in this case, the number of measurements minus 1. Very simple formula here. And in your book, there's a lengthy discussion about some technical nuance of the t-test, and they're doing it to determine concentrations of CO2, etc. You can safely skip over that portion of the discussion while it's still very important to take home these points. Notice that this is what I mean by there's a different student curve for each degrees of freedom. You can see when there are only 4 degrees of freedom that the curve is flatter than a normal curve. It's always the case that the student's curve is flatter than a normal curve. But as you increase your degrees of freedom, the student's curve resembles the normal curve to an increasing degree. And this is an important point and one we're going to revisit again later. Remember, you can use the curve when under the following circumstances. The data are like draws from a box. So there's simple random sampling is the point here. SRS for simple random sampling. If the standard deviation of the box is unknown, then you need to use the student's curve. Furthermore, if the number of observations is small, then you can't estimate the standard deviation of the box accurately, so you have to use the student's curve. And it's also a requirement that the histogram for the contents of the box looks generally like a normal curve. It's not too different from the normal curve. Okay? So this is our first alternate test, but we can use the z-test and the t-test when we have a one sample comparison, and just their use will vary based on these circumstances. As you can see here, there's a nice decision tree for how to decide what data to use. If the amount of data is large, then you use the normal approximation. If it's small, you can follow this decision tree to help you decide what to do. If the histogram contents of the error box is known, and different, there's all these different options. The histogram for the contents of the error box is unknown, but not too different from a normal curve, then use the t, or the student's curve. If the histogram for the contents of the box is known, but it's different from the normal curve, then you need to consult a statistician. You don't have the skills to do it based on this class. If it's known and it's very similar to the normal curve, then you can use the normal approximation, just like up here. I recommend practicing using this decision tree. Things like this, tools like this can be very helpful when you're deciding what test to use. In summary, the test of significance helps us get at the question of whether the observed difference is real or just chance variation. And when we make a test of significance, the null hypothesis should be set up as a box model for the data. And that null hypothesis always says that there's no difference between your sample and the box, at least for the types of tests we've already discussed. And the alternative hypothesis is another statement about the box, a statement wherein you say that it's different, that the box has a different mean or frequency, group representation, depending. We then use a test statistic to measure the difference between the data and what's expected based on the null hypothesis. And we can use the expected value in the numerator and compute that directly from the null hypothesis. If in the null hypothesis it determines the standard deviation of the box, you can use that information when you compute the SE in the denominator, but otherwise you have to estimate the SD from the data. So and finally, the observed significance level, or the p-value, is the exact, or the chance of getting a test statistic that is as extreme or more extreme than the observed statistic. So it's giving us this is called P for probability, and it's giving us the probability of getting a test statistic as extreme or more extreme. And that probability is computed under this basis that the null hypothesis is right. So in that sense, the P doesn't give you the chance that the null hypothesis is right. It's just telling you the chance of observing a test statistic as extreme or more extreme. When smaller values of P are better evidence against the null hypothesis. They tell us that something else is operating, not just chance variation, but there's some other way to explain the difference between these. And when the sample size is small, remember to use the t-test. So this is just the beginning of our discussion on tests of significance, but throughout the various tests we'll look at, we'll use the same hypothesis testing model through the whole, for each test. We'll just have vary a little bit in terms of the few different possible research scenarios. And this is one of my favorite quotes from all of the ones we've looked at yet, and I think it's pertinent to our current discussion, because a subtle thought that is in error may yet give rise to fruitful inquiry that can establish truths of great value. I find this very true because when you're setting out to do an experiment, sometimes we find very important results by accident, expecting to look for something else, but en route to looking for what we came for, we can find out something else that's really incredibly important. So good luck, and keep in mind that this also applies to thinking about how your own process here. Maybe you made a mistake at some point in this class. I know most people have, certainly everyone has, but that mistake helped you better realize your how to fix that mistake and help to build into a better understanding.